Hi, welcome to my talk, the EMV standard, break, fix, verify. My name is Jorge Toro, and this is joint work with David Basin and Ralf Zasek. We are security researchers at ETH Zurich. So what's EMV? EMV, also known as chip and pin, is the international protocol standard for smart card payments. The standard was founded by Europay, MasterCard, and Visa, and later some other card networks joined too. There are currently more than 9 billion EMV cards in circulation worldwide, and the standard has been advertised as to offer security to cardholders. So what's this security to cardholders? What is protection to cardholders that the standard is supposed to offer? The standard is supposed to provide assurance, the assurance that high-value purchases are protected by a PIN. The PIN is a secret number that is only known to the legitimate cardholder, and therefore should offer protection to high-value purchases, right? Well, in this work, we'll show that this is not the case, namely that indeed criminals can bypass this PIN verification, therefore violating the fundamental security goal of the standard. We can summarize the contributions of this work as following. We have developed the first comprehensive model of EMV. We did so by using the model checking tool Tamarin. Using our model, we rediscovered existing vulnerabilities, but we also found new issues. In particular, we found a critical security issue that leads to a PIN bypass. We proposed and machine-checked fixes to the issues found, and we have disclosed them to the vendors. In particular, the fix that we proposed to the PIN bypass does not affect the cards in circulation. Let me give you now a bit of background. The EMV transaction is typically split into 4 phases. In the initial phase, the card and the terminal agree on the application to be used for the transaction, and also they exchange some card and transaction data. Then there is offline data authentication, in which the terminal performs a PKI validation of the card, and this can be done using one of 3 methods. The methods are static data authentication, or SDA, dynamic data authentication, DDA, or combined dynamic data authentication, CDA. We'll talk more about them later. The third phase is what is called cardholder verification, and in this phase is where the terminal checks that the person presenting the card is indeed the legitimate cardholder. There exist various methods for this, and some of them include the entry of a PIN, and this PIN can either be verified by the card, and this is what is called offline PIN verification, or it can be verified by the card issuer, and this is what is called online PIN verification. There is also another method which is particularly relevant for this work, and it's the one called consumer device cardholder verification method, which is intended for smart devices like smartphones or smartwatches. In the fourth phase, in the final phase, is where the transaction is either declined or authorized or accepted, right? If the transaction is accepted, this can be done either offline by the terminal, which means that the terminal decides to accept the transaction, and this is typically the case where the transaction is of low value, right? The amount of the transaction is low, or the transaction can also be authorized online, in which case it means that the terminal needed to contact the card issuer to authorize the transaction, right? Tamarin is a model checking tool that has been used widely, that has been used by a number of researchers, and relevant works that use Tamarin are those including analysis of real-world protocols like 5G authentication and also TLS 1.3. In Tamarin, one defines a system, one specifies a system, which is the protocol, by using multi-set rewriting rules. These rules define a label transition system that represents the protocol executions. Then a property is specified, a property of interest that one needs to check if the system holds it, right? If the protocol satisfies this property, and this property is specified using first order logic formulas. And the tool will try to find a counterexample for the property according to the system specification. If it does find a counterexample, this means that there is an attack. The proof can also produce a proof saying that it is not possible to find a counterexample for this property, right, for this security property, or the tool can run out of memory or time, in which case the user has to provide some hints for the tool to terminate. For this work, we consider three main properties. The first one we consider is what we call bank accepts, which says that every transaction that the terminal accepts will not be declined by the bank. The second property we consider is what we call authentication to the terminal, which says that whenever a terminal accepts a transaction, it is the case that this transaction was authenticated by the card and also by the bank. The third property that we consider is what we call authentication to the bank. And it says whenever a bank accepts a property, it is a transaction, it is the case that the terminal authenticated and also the card did. We specify the authentication properties using the classical injective agreement property. So let's take a look at the results that we got for EMV contact transactions. Here we have a table showing the results, and the rows here are what we call target models, which are basically a combination. So one target model is the result of one specific authentication method plus one specific cardholder verification method plus one type of authorization of acceptance of the transaction, right? Either offline or online. And the combinations of all these gives us like a partition of the EMV execution space, right? So the first thing we notice is that only transactions using combined data authentication, which is the latest authentication method, are secure. I mean, transactions using this authentication method and online PIN or no PIN as cardholder verification are secure. Transactions using any form of offline PIN verification are vulnerable to a PIN bypass attack, and this was already reported more than 10 years ago by Murdoch et al. And also at Auckland in 2010. Transactions that do not use the combined data authentication method are vulnerable to a violation of our property called bank accepts, the first property that we mentioned earlier. And this is and the way that this can be exploited is by employing the attack will simply make the terminal accept transactions that will later be declined by the bank. And we also found some other issues related to secrecy. In general, one can say that exploiting these issues, weaponizing these issues in practice is kind of challenging because one has to compromise the card terminal channel, which is by definition a contact-based channel. So let's take a look at the results for the contactless version of the protocol. Good news is that common MasterCard transactions are secure, but common Visa transactions are not. So let's take a closer look at the Visa protocol and see what the problem is. In the Visa protocol, the card's choice for cardholder verification method is encoded in what is called card transactions qualifiers. And this is a data object sent from the card to the terminal in response to one of the terminal's commands. It turns out, as specified by the Visa protocol, that this CTQ value, this card transaction qualifiers data object, is only protected by a signature by the card, and this signature is called the signed dynamic authentication data, SDAD. But it turns out that most Visa transactions don't actually use this signature. They don't need to have this signature involved in the protocol, right? And this means that one can tamper with the CTQ, and therefore one can tamper with the CVM. So what does that mean? It means that one can change the cardholder verification method chosen by the card and conveniently change this into something that might help the attacker, right? So, and this is exactly what we did, right? To weaponize this issue, to demonstrate that this issue leads to a practical attack. And we implemented a man-in-the-middle attack. We implemented an Android app that builds a man-in-the-middle attack on top of a relay attack architecture. So let's assume how does this attack work? So let's assume we're in a high-value transaction, right, where the PIN is needed. And in this case, the terminal will, and we have reached the state of the protocol where the terminal is going to verify the cardholder, right? And then because we're in a high value transaction, the terminal will send a command indicating, yeah, I need to verify, I require to verify the cardholder because we're in a high value transaction, right? And in a normal execution, the card will send back a CTQ value with indicating that online PIN is required, right? The card will say, okay, let's do online PIN verification. But here's where the attack comes in, right? So the attacker just changes the CTQ value to instruct the terminal that online PIN is not required because the consumer device, the cardholder has been verified on the consumer device. So what does this mean? This means that basically the terminal believes that the execution is being made with the phone, with the smartphone, and not with the physical card, right? So therefore, no PIN is needed. Okay, so let's watch a demo now. So we implemented an Android app using 2 phones. Here you see 3 phones because the phone on the left-hand side is the interface for the terminal. But in reality, these 2 devices will be simply just the terminal, right? The payment terminal. All right, so this is a transaction of 200 Swiss francs, and it went through without entering the PIN, right? Okay, so we got a lot of media attention, right? And this was a very interesting process. Okay, so let's try to fix this, right? So whenever we find a problem, it is good to try and fix it, right? So let's first recall the problem. The problem is that there is a signature that is not being used in the Visa protocol. So therefore, the cardholder verification method is not protected and can be modified, can be tampered with, right? So if the easy fix is simply to use that signature, right? So it's there for something, so let's use it. And the way that one can have the card signing and providing the signature is by simply setting 1 bit in one of the terminal's commands. And good news about this is that it can be deployed on terminals without having to change anything on the cards that are already in circulation, right? So this is, in theory, cheap for banks and the banking infrastructure in general to deploy, right? This was not all. We found some other issues. For example, we noticed that offline low-value transactions are not secure. Most offline low-value transactions are not secure. And the way that one can weaponize this is by having an attacker fooling a terminal into accepting a transaction that will later be declined by the bank. And why is this possible? Because there is some lack of authentication in the offline version of the protocol, right? And we didn't test this in the wild. We didn't try this attack in practice in the real world, because this will actually mean a fraud, right? We will be defrauding the merchant if we succeed in the attack. And yes, there are fixes for this, and we have described them all on the paper, and you can go and check them out. But in general, these fixes are not as simple as the one that I mentioned before, and they do require reissuance of cards. Conclusions of this work is that formal verification must accompany protocol development and standardization efforts, because if you're building an infrastructure, critical infrastructure, you have to get it right, right? We as humans cannot possibly deal with the huge amount of execution steps and branches that a complex system has. And in general, there is evidence that existing verification tools are up to the task. So please visit our website to get more details on this work. And thank you very much for your attention. I hope you have enjoyed the talk.